Hi, this is David. Welcome to Part 2, Topic 5, Tuckman's Chapter 10, which is a continuation of Tuckman's Chapter 9, all of which are on short-term interest rate models. The associated workbook is Topic 5.29.10. That's because it's reading 29 in Topic 5 of Part 2 FRM and Chapter 10 of Tuckman. The workbook contains 3 worksheets because there's 3 models that are reviewed. However, only the Cox-Ingersoll-Ross is tagged as medium above the others because this is the most, arguably the most useful or popular of the models discussed. It's also called Model 4 in the Tuckman reading. And so just to recap where we are, this Chapter 10 continues from Chapter 9, all of which are a review of short-term interest rate models, from a really basic to more sophisticated. Chapter 9 reviewed 4 models, and you might notice what they have in common is an assumption of constant volatility, or what we want to call annual basis point volatility as the input. That didn't change in any of the Chapter 9 models. What changed is the treatment of drift, starting from a Model 1 that assumed no drift up to maybe the first realistic model, the Vaschek model, that introduced mean reverting drift for the short-term interest rate. Then Chapter 10 turns its attention to the volatility assumption and liberates us from this assumption that volatility is constant. And so starting with Tuckman's so-called Model 3, where he assumes, or where we assume a model that can have a time-dependent volatility. And so that would be as characterized here. The form is familiar, similar to the other models, although the key difference here is this factor for time-dependent volatility. You'll notice it's e raised to an exponent here of negative alpha times t. It's not d of t, but it's t. So it's really where we are in the interest rate tree. And so this factor here is different from anything we looked at in Chapter 9, because now we have a volatility that is time dependent. It's also, we can simulate it out randomly, because you'll recall d of w is a random normal variable. So it really acted as before. It takes a standard random normal variable, that is to say, it starting with a uniform random variable from 0 to 1, an inverse transformation converts that into a random standard normal variable with mean of 0, variance of 1, and then it scales that by the square root of the d of t. And so we end up with a time-scaled random